Well, welcome to this online revision session for AQA FP4, in which we'll be doing the January 2011 question 3 on the solution of linear equations. See, this question has two parts. In the first part, we've got to determine the values of t, where t, you can see, is present in some of the coefficients of x and z. And the values of t we're looking for are the values of t which give us a situation in which the three equations do not have a unique solution. Remembering, a unique solution will be when the matrix, if we put it into a matrix form, the matrix has an inverse, so that we then determine a single unique point solution. So if the matrix does not have an inverse, then the determinant of that matrix must be 0. Having found those values of t for one of them, we then find a relationship between a, b and c, so the system of equations is consistent, that is, it has an infinite solution of some sort. Well, if we wrote this in its matrix form using the coefficients of x, y and z, we know that that particular matrix must have a 0 determinant for it not to have a unique solution. So if we write down what this matrix is, we're going to have t, 2 and 3, 2, 3, and 5, 3, negative t, and t plus 1. And this determinant must therefore be 0. Well, it probably won't make much difference which line we use to expand this. Looking at it, I think probably we'll just use the first column. And so if we do that, we're going to get t times the determinant of 3 times t plus 1 minus 5 times negative t. So that will in total give us 8t plus 3, which when multiplied by t will give us 8t squared plus 3t. Then if we move across or down to the next one with the 2, remember in this one will be negative because of the plus minus plus in the grid that helps us determine these values. We've got negative 2 then times 2 times the t plus 1 and 3 times the 5. So that's going to give us 2t plus 2 minus 15. So that's 2t minus 13, which when multiplied by negative 2 is going to give us minus 4t plus 26. And then we've got 3 times the determinant of 2 times the minus 2 and 3 times the 3. So that is going to give us minus 6t. And then it's minus 9 times that 3, so that's minus 27. And this has to equal 0. So we're ending up here with a quadratic. So we're going to get 8t squared, and then we've got 3 minus 4t is minus t minus another 6t, so that's minus 7t. And then 26 minus the 27 gives us minus 1 equals 0. Obviously there's other ways to expand this, but obviously you should end up with that same answer. And so now if we factorize this expression, well, we know it to get the negative 1, it's going to be a negative 1 and a plus 1. And so to get that minus 7t and to get the 8t squared, we're going to need an 8t and a t, which must be which way round. It's going to be the 8t in here to give us enough to give us the minus 7t, and the t will go in here. So that's factorising my inspection, and so that gives us two possible values of t. Either t is 1 or t is negative 1/8. Okay, well, why did they give you the 3 marks? Well, a method mark for identifying that you need the determinant and having the correct coefficients in there. For then equating to 0 and solving the quadratic, you'll get a method mark, and then an accuracy mark then for obtaining the correct values of t. Into the next part then, it says using the integer value. Well, the integer value we're going to use is t equals 1. And so that will then change our system of equations to the following. We will have x plus 2y plus 3z equals a. And then we've got 2x plus 3y minus z equals b, and then we've got 3x plus 5y plus 2z equals c. So, what do we know? Well, with this system of equations, we can see that if we add them together, we'll add the first two together, we'll get 3x, 5y and 2z. So if we add 1 and 2 together and then take them away from number 3, we will then have the following. Will we not? We will have, let's just write down what we said we're going to do. So we're going to add 1 and 2 together and take away number 3. So it's 1 plus 2 minus number 3. And so we can see the x's cancel out, the y's cancel out, and the z's cancel out. So we get 0 equals a plus b minus c. And so for those to be consistent, they can only be consistent if a plus b minus c equals 0, or in other words, a plus b has to equal c. If that's not the case, if it wasn't equal to 0, then you'd have a scenario where nothing was equal to something, which obviously couldn't be true. So again, what do you get? Substituting the correct integer value to get these equations. I'll give you a mark, then a method mark for eliminating the x, y's and z's from those equations, and then determining what this relationship is between a, b and c will give you your 3rd mark. Hopefully you found that solution helpful. For more examples and further support in your revision, please go to the Further Maths Support Programme website.